Hey, welcome back. In this course on C++, we have discussed conversions or typecasting quite a bit. We have spent quite some time on that, and that's because C++ is a strongly typed language, and that simply means it has some strict type rules. And with that, if you do not have explicit type conversions, you may have warnings or errors, that is, during compilation. So a summary on some of the things that we have discussed so far in the course here on C++. I talked about explicit type conversions, or typecasting, where we can convert using the C language style cast notation, or the functional syntax, where we have the type on the left and then we can pass in what we actually want to convert, the expression that we want to convert to the specified type. But then I also mentioned it's difficult to search for where you actually do conversions in your file, in your source file, and that we also have more type-safe static casts used in modern C++. I mentioned we have the static underscore cast, and we can pass in the type that we want to cast or convert to, and then we pass the expression that we want to convert between parentheses. Now at this point, hopefully the syntax will be more comfortable to you, because at this point we are familiar with the template syntax, right? We also had some lessons where I discussed the conversion constructor, where we can have some constructor that will convert a single argument of a different type into the constructor's class type. We also discussed operator overloading and how we can have a conversion assignment operator, which will take in a constant reference to the right-hand operand, so whatever we have to the right of the assignment operator. We also discussed the conversion function or operator, or also known as the typecast operator. So we have discussed quite a few ways of how we can convert between different types, because again this is important in C++. Now in this lesson I want to spend a bit more time talking about static and dynamic casting, and so what the differences between those are. The cast operators that we'll discuss in this lesson, such as static cast and dynamic cast, are unary operators that convert one actual parameter, so the argument that we pass in between the parentheses, to the specified type argument type. Right, we have this template syntax that we can see with the static cast, and the type argument between the angle brackets is what we want to cast or convert to, basically. So with the static cast, we can perform pointer upcasts and downcasts. It also performs type checking to ensure safe conversion. However, the static cast operator is a compile time cast operator, so no runtime checks are performed to ensure that the pointer is pointing to a complete object of the pointer type. A runtime type check is an overhead for the dynamic cast, which we'll discuss in the next lecture, so the static cast does not have that runtime overhead. However, because we do not perform that runtime check, the static cast operator is not as safe as the dynamic cast, and so the programmer must ensure type safety with static cast. Another interesting note is that static cast can invoke implicit or explicit conversion constructors. Some simple examples using the fundamental C++ types. I have a double here, d, which I initialize to this value here, pi, and then I have implicit conversion. So we have seen the implicit conversion before. This is going to implicitly convert the type of d, which is double, to short, and then assign that value to short. You can have some data loss with that. As we can see here, when you build, you will get a conversion from double to short. Possible loss of data, as we've seen before. Also in the output window, conversion from double to short, possible loss of data. We have seen those warnings before, and you can avoid those warnings. Get that out of the list there using explicit C style cast. I'm doing this style here. We have also seen the functional style. And then we can also do an explicit cast with the static cast. Using the syntax here, static cast, we pass the type that we want to convert to, in this case integer, between those angle brackets, and then between parentheses we have the argument. In this case d is of type double. We want to convert from that type double to int. So that is an example with the fundamental types. Now we can also convert pointers, as we'll see in upcoming examples. Let's look at an example of something that we want to avoid in C++. I have two different classes here, entity1, entity2. Both of those have a public toString function that will simply print out the relevant string. So entity1, toString for entity1, and for the class entity2, in the toString we have entity2 toString printed out, in the case where we invoke those functions. Alright, so in the main function, I instantiate entity1. I call that E1 here, and then I actually have a pointer to an entity2 type, which I'll simply name PE2 for pointer to an entity 2. Now this is a simple example, but of course production code can get complicated. But for example, let's say you have some object and you want to assign the address of this to a pointer of a different type, right? For some reason, you may get the idea that you want to do that. For example, let's say we want to assign the address of E1, this entity 1 here, to this pointer. Now again, the types are different, right? This is entity 1, this is a pointer to an entity 2 object. Now we actually get a red squiggly, and this will state that a value of type pointer to entity 1 cannot be used to initialize an entity of type pointer to entity 2. So you might think, okay, well, I can use explicit type conversion to convert the type. So to demonstrate, and you can see that that squiggly will go away. So we have the address of E1, which is of this type entity 1. So we convert the pointer, we will convert to pointer of entity 2, and now of course we can assign that to this here because this is a pointer to an entity 2. Now you may go and do something like this. I do PE2, so that pointer, from that pointer I invoke the toString function. So of course this is a problem. You do not want to do this in C++ because you can have unpredictable results, because with the entity 1, for example, let's say that does not even have the toString function, right? Also notice, just to emphasize here, that class entity 2 does not derive from entity 1. So we do not have an inheritance hierarchy here. These are two completely different classes. They do not have any sort of relationship. Okay, so this is something that you want to avoid in C++. If you build and run, you may see some sort of result like this. But for example, if I undo here, let's go and remove that toString. Now we may get an error. So again, the thing is, you may want to invoke based on the actual object. So in this case, E1 is actually an object of type entity 1. Alright. So previously, I'll just undo here, build and run. We actually get the toString on the second entity here, entity 2. So of course, this is one thing that you want to avoid, and we've seen to some extent how you can do that with virtual functions and with polymorphism. But again, this is not a case where we have polymorphism set up, because these are not related. We do not have an inheritance hierarchy here. Entity 2 does not derive from entity 1. So again, something that you want to avoid, and we can instead use static casting and dynamic casting. Alright, so instead of doing this here, I will use static cast instead. So I will copy the pointer PE2, which again is a pointer to entity 2, and I will use static cast, casting from the whatever the type of E1 is, the address of that, and I will cast to a pointer to entity 2. Now we can see red squiggly here. If I build, we actually get an error. Cannot convert from pointer to entity 1 to pointer to entity 2. Types pointed to are unrelated. Conversion requires reinterpret cast or that functional style cast that we've discussed before. So this is really useful. Static cast performs type checking, which will disallow this sort of cast, this sort of conversion. Whereas as we've seen with the C style or functional style casts, that type checking is not performed. Alright, so this is really the benefit and the use of static cast. Just a couple of topics that I want to reinforce before we continue. We've talked about upcasting and downcasting. Upcasting being safe because let's say you have a pointer to a derived class and you assign a new derived object on the heap, and then you upcast from a derived to a base class pointer. That's fine, because if you have a pointer to a base class and you assign to that the address of some derived object on the heap, and then you try and access some member from that base class pointer, that's fine, you won't have any issues. But if you have a downcasting situation where you have a pointer to a derived, but you have some base class, the address of some base class object assigned to that, and you then try and access some member from that derived pointer, that member may not actually exist. So from derived you can try and do some toString function, but the actual object on the heap is a base class object, which may not actually have the toString function, right? So we have to keep upcasting and downcasting in mind, the differences, and also what the actual object is that we have allocated on the heap, or simply what type the object is that the pointer is referencing, because of course we are not always allocating on the heap. Now, in previous lessons, we discussed the fact that a derived class is made up of the base part and the derived part. Alright, and how the construction and destruction is handled. Okay, now we can have a pointer to an incomplete object of the pointer type. Don't get this confused with the error that you have when you have an incomplete type. So, for example, you do a for declaration of a vector struct. Now, if we declare a pointer to a vector, then that's fine because it's going to use the for declaration. And then if you try and instantiate the vector class, the vector struct that is, so we have vector location, for example, you will get an error because we have an incomplete type with that. The compiler does not know the full type, it does not have access to the full type, it does not know how much memory to allocate for that particular type. But a pointer is fine because a pointer is just a pointer and it will have the same amount of memory as any other pointer because it simply stores an address. Now, getting back to this, a pointer to an incomplete object of the pointer type. What does this mean? We have to sort of understand this before we continue on here. This typically happens when you downcast from a pointer to a base to a pointer to a derived, alright? So in this example, we have a pointer to a base and we allocate on the heap an object of type base. Then we want to downcast from the base to the derived for some reason. So we have a pointer to a derived type. Then we want to downcast that pointer to the base to pointer to derived, in case we want to modify that type. So the issue here is, what exactly if you give this some thought? Well, moving on to the next slide here, it is always important to remember what object we have on the heap, so the type of the object on the heap. Because from the pointer to derived, that p derived pointer, if you want to access some member or some member function that is not actually part of that base class object that is on the heap, then you can have an access violation, you can get garbage, and so on. So you can have runtime errors with that. Of course, if you have a pointer to a base and on the heap you have a derived object allocated, then you won't have an issue because from the pointer to a base, you will be able to access all of the members from the base class part of that derived object that is on the heap. So that is fine. But if you have a pointer to a derived and you have a base class object allocated, then of course you can have some issues. So that is referred to as having a pointer to an incomplete object of the pointer type. In this next example, I have a base class and a derived class which will publicly derive from the base class. I have some toString function and a private integer x. The toString function will print out the x member. Alright, so in the main function now I have a pointer to a base type and I allocate a new base object on the heap. Now the next section is not safe. Alright, we have a pointer to derived and then we do static cast. We do pointer to base, so we convert that type, which is pointer to base, we convert that to pointer to derived. Then from the derived pointer, we try and do toString. So this is not safe because the derived can have members that are not in base. Alright, so from your derived pointer, you're trying to access things that may not actually be in the base class. So what happens if we build and run this? Well, we actually get garbage. So this can be an issue if you have a member that you try and access in this way, some function. Well, you can have an access violation with that, so you want to avoid this sort of thing. And so the point of this is static cast is not actually going to help you with this. And so you'll have to pay attention to the object that you have on the heap, because this is an example of a pointer to an incomplete object. Alright, you have a pointer to derived, but the actual object on the heap is base. So the pointer is a pointer to an incomplete object of the pointer type. So in this case, pointer to derived, we do not have a derived object on the heap. Whereas if we did this in the other way around, if we had a pointer to derived, and down here we had a pointer to base, but we had a derived object on the heap, then that would be fine because all of the things that we can access from that pointer would have been in the derived object which is on the heap, right? So you have to keep these things in mind, what you have on the heap, the pointers that you are working with, and whether you are upcasting or downcasting. In the lesson on inheritance, we discussed public, private, and protected derivation, and we discussed the fact that the access specifier determines member access in derived classes. We also discussed the fact that the access specifier can modify the relationship between the base and the derived classes. So for example, the public access specifier models an ESA relationship. So a derived class is a base class, whereas the private and protected access specifiers do not model an ESA relationship. So a derived class is not a base class. So what does this mean for a second? Well, if you do type checking, for example, with the cast operators, the access specifier will have an effect on that. It's not going to pass unless it is a public access specifier, which again models an ESA relationship. In this example, I have the class base and the class derived, which publicly derived from base again. In this case, I do not have any special members, any specific members. This is just for demonstration purposes. And in main, I have some pointer to a derived, and I can allocate on the heap if I want, or I can simply instantiate the derived object and then assign the address to the derived pointer. But in this case, I'll just go ahead and allocate, also eventually making sure to delete to deallocate that object, whatever the pointer is pointing at. In previous examples, I forgot that step, but that's an important step that we have to remember as well. So here we can do a C-style implicit conversion. We've seen this before, and in this case it's going to implicitly convert this pointer type derived to pointer to base. Then we have an explicit C-style cast. So we can do a pointer to derived, whatever that type is, we convert that type to pointer to base. Then we assign that to this pointer right here, which is of type pointer to base. Then we can also do static cast. Again, between the angle brackets, the type argument is pointer to base, and then we pass in the actual argument is p derived, so that pointer we want to convert the pointer to derived to pointer to base, and then we assign that to this pointer 3 here, which is a pointer to base. So if I build and run, we are not doing anything specific here, but that will actually build and run. But if we change the derivation, so in this case we have a public derivation, so derived is a base, right? But if we change this to protected or private, you will notice that with the implicit conversion you will get an error here, and then also with the explicit static cast as well. Build and run, and notice we get that error. Typecast conversion from pointer to derived to pointer to base is inaccessible, and the same with the static cast as well. And that's going to be the same with private. Build and run, we get a failed. Alright, so that is again because when you change that from public to private or protected, then we change that inheritance relationship. Derived is no longer considered a base, so that here's a relationship no longer holds. One final example to wrap up this lecture on the static cast. In this example I have some class entity, and I have a conversion constructor, a conversion assignment operator, and also the conversion operator. Just another example on some of these. We have discussed these operators and the constructor before, so to convert between types. So this is one more example on that. And then so for the conversion constructor, I'm going to print out conversion constructor invoked, and then I will assign the parameter to the member. I have in the private section an integer called the member. Alright, then for the conversion assignment operator, we overload the assignment operator, and we go and put out to the console conversion assignment operator invoked. We assign the argument here, so the right hand operand we will assign to the member, and then we return a reference to this. Then for the conversion operator, we put out to the console conversion operator invoked, and we return the member. In the main function, I go and instantiate entity, and then we can do some assignment. So we assign 55 to entity, and of course this is going to use our assignment operator. So actually let's just build and run this quickly here. So you can see we have a conversion constructor invoked. We have the conversion assignment operator invoked next. So here it's going to do the conversion constructor. It's going to convert this integer to construct the entity. Here we have an assignment, so it's going to use the overloaded assignment operator with that integer. But here we are actually going to do console output, and then we have entity member is, and then we simply put entity here. So of course that is going to use the conversion operator, alright? And so we have again a conversion assignment operator invoked, conversion operator invoked, and then we get that printout. Entity.member is 55. Alright, so following that we have this here, staticast, where we assign entity, we pass in the object entity to staticast and we pass in int, so we want to convert from entity to this int type and we assign that to int. So because of that we get the conversion operator invoked. Next we get the conversion constructor invoked, and that's because in this statement we are trying to convert an integer 47 to entity. So we do staticast and we want to assign that to entity, alright? And because of that again, we get the conversion constructor invoked. Finally, we'll get the conversion operator invoked and we print that out again. And that's because down here we have entity, alright? So it's going to use the conversion operator and then we print this out. So again, it's going to use the conversion operator and then finally we print that out. So that is the output that we get. And why we invoke which constructor or assignment operator, so which conversion function basically we will use in which situation. So just another example on that, and also just to emphasize the fact that staticast will actually invoke the conversion constructor or the conversion operator, okay, depending on what you do. Alright, so we have seen quite a few examples in this lecture. I could have added a couple more examples, but you should get the idea from these, and hopefully you have a better understanding of the staticast operator at this point.